No, my plan was thwarted.
There is some stuff. You know, I don't know, Dan, maybe you can counter this, but today, I started thinking about how many spacecraft are en route at the planet, going to be launched in the next month.
Yeah, it's crazy.
I think we're at some time in space exploration history
Yeah, it's amazing.
that's unparalleled.
It's amazing.
I can't think of anything that's been so many things. And not the US, but
No, everybody, I
European.
mean, all of us together globally. There's,
Yeah,
there's a lot
globally.
out there. It's just amazing.
We are at some epic point. And I'm sure I'd write that, and somebody would go, no, back in, but I can't think of.
But it's not true.
Huh?
It's not true that
It's
we're,
not true?
commercial and government
Oh,
launches have gone
yeah,
nuts.
Everything. I mean, it's just, there's an amazing potpourri of stuff going on in space exploration in our lifetime, like this month, that is unprecedented. And let me just yak for a second. I think one of the coolest things I've been following lately is Japan. They are on target. They have arrived at an asteroid with their Hayabusa 2, doing some cool things, closing in. Not only closing in, but making it happen. They're going to go retrieve some kind of material out of the asteroid that they just close in on. And look at these pictures. This is like real time shadow of their spacecraft on the asteroid. They are down deep, and they are so excited. And again, I'm just that little area that they circled off there is where they're going to do the landing to collect asteroid material off this asteroid and then bring it back to Earth. And look at these pictures. Look at the shadows. They're so down. They are so close to making this happen. And again, I want to emphasize space activities are not US and they're not NASA. There are so many things going on. I find this so exciting about them pulling up on this asteroid. But not to discount the United States. What's coming up? Here's OSIRIS-REx. We have our own asteroid mission from NASA, closing out on Bennu, a new asteroid. Here's a close-up just the other day. They're closing in day 2 with a NASA mission coming into an asteroid. You're gonna learn more and more about asteroids. Cool thing, November 26th, this month, Mars, Insight, built by Lockheed Martin, local. How many people from Lockheed Martin? We'll attempt the multiple Mars landings that we've done in the past, but this is a cool one. This is coming in just this month, in a few weeks away. It'll break around, it's going to break above Mars and land. And there's the Elysium site it's trying to get to. Hopefully it'll be a successful landing. And this particular spacecraft is built for seismometry, learning about the interior of Mars. To be callous, I really don't care what this thing does. I think anytime you land on Mars, you learn something new, and this is going to do something else. And I'm very hopeful that this spacecraft lands okay. There's a lot of interesting sidebars to this mission don't discount that it could be a failure, don't discount that it could be a success. Anyway, it's a soft landing on Mars coming up November 26th, so this is real time, in our time, and it's happening. I'm worried about my opportunity Mars lander. We're not sure if we hear anything from opportunity. This has been on the planet for many years. The dust storm came, covered its solar panels. We're not sure if it's alive or dead. Shot Propulsion Lab is still sending messages. Can you wake up? Can you wake up? It may be alive, it may be dead. We don't know. Okay, keep an eye on that one. It could be dead.
You monitor that every morning.
I
right?
watch
So
it
that's
every
why-
morning.
when
I'm
it's
hoping for
7
pictures. Nothing's happening. We'll see. And here's some cool thing. Here's our other Mars rover on the red planet, and Curiosity, multi-ton thing, lost it. It's sitting there. It had some brain drain. The damn thing. It just had a memory lapse. It's been there since 2012, and also went into a memory lapse. There's something happened to it. They brought it out. It's coming out of a coma, basically, on a memory problem. And it's starting to relay more images and data, but it was out for quite a while. It had something happen. And here's the story in my mind, and don't believe me. Something that Curiosity has picked up is some interesting things that in the astrobiology side, this is a new image from Curiosity because it came out of its lapse. And it is found something that we can't quite figure out what that is. Could it be something that tells us about life on Mars in the past? Which is why it was sent there. And there are people, my email was clogged today with stuff, and people thinking that maybe Curiosity has picked up some imagery that shows some kind of astrobiology, life in the past on Mars. And then I go to the downside of this, and there's a lot of people saying, no, this is some other kind of phenomenon. This is something else. And watch that story. Watch that story.
What's the scale of
It's bigger than a football field.
No.
Yeah, I know, it's very small. These are pretty much very small residue
What is
on
those
Mars. But
signs?
they've been picked up by Curiosity, and they're spending some time, as a couple days ago, on investigating this. I'm just saying, in my view, Mars has already told us, and this is my view, and I'm in the minority. Mars has got some signals about life on the past of Mars, and we discount a lot of these kind of phenomena too soon, I think, because we don't get, again, I'm biased, but I think there's something else that we're seeing in some of these pictures that indicates something else is going on with a water-laden planet, and where life, may have evolved and died. And we're seeing some residue of these things. So it's a controversial step to say, well, we see pictures of this. And I'm just saying, watch this story. This is something that's going to be aggravated assault. Okay. Now, this is not a real picture, but this shows you what's happening in the popular culture about the next year with the 50th anniversary of landing on the moon. 50 years ago, we were on the moon. People were walking on the moon, not with kids, but this kind of stuff. This is one company that's advertising, you know, the whole 50th anniversary of the moon landing. And you're gonna see a lot more of this, and I'm gonna be talking about this as we move on next time around. 50 years ago, we landed on the moon. America pulled off this adventure. There was a unbelievable story coming about who else is coming. The moon is the target, and it's a space race in my mind. We have a Sputnik effect coming. China, particularly, is going to be very dominant about moon exploration, and we're getting our act together. There's going to be a world, moonwalk coming, and we're going to be treading our way to the moon, back to the moon. And meanwhile, I'm doing my due diligence here because I've seen all these episodes of what National Geographic, they're gonna, their second season of a Mars television program. You won't believe what's gonna come out of this one. Very different from the first season. There's some signals coming out of this series that has a lot to do with Earth. And it's pretty compelling. But anyway, this is the beginning of a new series too. I'm hyping this because I'm attached to it in some way. But scouting that, I think it's worth a watch. It's a great adventure of 6 parts in the next, from November 12th. We'll see Mars in a different way than we've seen it, and what it could be, and what it shouldn't be. I'm leaving you with this. I took this out of my aircraft going over to Phoenix the other day. That's not a good sign.
It says, I was your pilot.
But look, I think the main thing I'm trying to say, there's so much happening. I don't think in my lifetime I've ever seen so much traffic going to other planets than we've got now. So much unbelievable imagery coming down from Jupiter, a spacecraft on the way beyond Pluto. We got China going to launch next month, going to the far side of the moon. I think we're in a really, I'm not even covering it all. I just don't think I can think of any time, unless somebody else has something else to say. I can't think of any time that this has been the most important time in space exploration history with robotic probes, that we've done so much at so much area, and we're there, and we're doing stuff. And it's just, I can't wait till next month to tell you whether these things failed or succeeded or whatever, but, we're trying. It's a great time for space exploration.
One question, is there, for any of you there, is there a reflection of any of the lights in the screen? Which ones? Can you tell? Maybe don't tell us. Or we can shut some of it off. Would that be, is that better? There.
Is that better?
Okay, and that's.
But can you see, like, us when we're up front? We know what she looks like, it's okay.
No, you should have seen me on Halloween. It was freaking. Nobody come to my house. Got a switch here. If y'all don't know me, my name's John Williams. I wish that I could say that I was related to that guy who created the cool music, but I have to say no. But I did take that cool picture.
Isn't that nice?
And why aren't it's gonna be anyway, well, there it is. So yeah,
You're the problem solver.
I don't know about that. I'm the problem solver. I'm also a NASA Solar System ambassador. So you have your own ambassador. So when the aliens come, they're going to take me. I volunteer. No. Me first. That would be cool, wouldn't it? But like Leonard, he does all the space news stuff, and I do all the astronomy stuff. And you know, Leonard was talking about how exciting things are with space news launching on rockets. I'll talk about some of that as well. But astronomy news does not stop. I mean, and it's not slow. It just is like, well, you know, maybe you don't know, but there's a lot going on. And we'll try to get through it all of them. Just kidding. I'm going to start here at Earth, and then I'll go to the far reaches of the universe. But the 30-meter telescope's being built. Well, it's not being built. Construction was stalled because of some court case. They're building this thing. It's one of the largest telescopes that we'll have on the planet on Mauna Kea in Hawaii. Native Hawaiians feel that there's a lot of telescopes on Mauna Kea. There's a lot of telescopes on Haleakala on Maui. And like a lot of places, they feel these places are sacred. And so there's these guys at the 30-meter telescope just won a lawsuit. Well, the court favored in their favor, it ruled in their favor. And so they get to start building their telescope again. This is like a $1.4 billion telescope. It's going to rival James Webb. It's going to rival the Hubble. But it's Earth-based, so we don't have to fix it from the ground when it's broken. And we just had that problem with Hubble. Hubble's been in orbit since 91. It was launched on a shuttle, and it was repaired by the shuttle 5 times. But we don't have a shuttle anymore, so we can't repair Hubble anymore. But their gyroscopes are old and started, wearing down, so it went offline. Wasn't doing science. But this was an image they took back in August, and it was one of the ones that NASA released saying, we're doing science again. And what's cool is this past week, they studied flares around faraway red dwarf stars. This is important because we're finding in the Kepler, which I'll talk about in a second, the Kepler data that some of these they're in what's called the Goldilocks zone. They're in the area around the star where liquid water can be liquid, and that may indicate life, or it may be if it were like life on Earth, we might find it there. But anyway, and they also, what else they study? Faraway galaxies like this. This is a gravity, they call them Einstein arcs. There's one of these quasars back here is a huge gravity well, and it curves. This galaxy is actually on the other side of it, far away, and it's curving that light. These are the things we're learning about, helping us understand the beginning of the universe and stuff. This is another image that NASA released, and I always have to share the cool images because they're just so darn neat. I mean, obviously I'm in love with Hubble. I created those whole star cards back there for you guys. So, we've also had problems with Kepler, and we know this was coming for a long time. Kepler's out of gas. Kepler is looking for extrasolar planets. It's staring at a tiny, tiny little piece of Cygnus tiny little part of the sky, and it's looking for dips in the light curves of all these stars. It monitors something like 150,000 stars for these differences. Out of the almost 4,000 stars that we've identified with planets, real planets, whether they're super hot, hot Jupiter spinning around the sun in 9 days or 9 hours, or even other smaller things that are rocky, perhaps, super Earths we're finding. Out of the almost 4,000, Kepler by itself has found 2,000. So I talked to this guy, his name's Bill Barucki. He came up with this idea way long, back in the 70s. And it's just an exciting project. But the search for planets won't end. We've got the James Webb Space Telescope in a couple years, and there's also TESS, which was launched earlier this year. And it'll be looking similarly to what Kepler's doing, looking at those light curves from space. And it's going to be monitoring something like 400,000 stars. So a bigger group of stuff. This is another image of it. In August, we launched what's called Parker Solar Probe. It's a probe to the sun. It's going to study the sun and the corona more specifically. The other day it broke 3 world records. Now it became the closest thing we've ever sent to the sun. And it's going to get closer. It's something like, I have my notes here. I don't want to be wrong. It's going to do 24 approaches. Right now it's heading for one that's going to be 15 million kilometers. It'll eventually get down to about 5 million miles from the sun, which is pretty exciting. After all those orbits, it's, so it's now 26.5 million miles from the sun. Now it's also the fastest moving object relative to the sun, 153,454 miles per hour. And then it's also, and these were set back in the 70s by a spacecraft called Helios 2. So it hasn't, and now it's also the fastest relative to Earth, which it took the record away from Juno, which is now at Jupiter. So more stuff. Watch this mission, just like what Lunar said. Watch all these. You have to watch all these missions. They're so exciting. Let's see. We had a new satellite launch, Columbo. This is a European Space Agency mission, and it's going to be studying Mercury, but not anytime soon. It's going to take 7 years to get to Mercury. It is going to use 8 gravity assists. 6 of those around Mercury itself. So it's going to use Mercury. It's falling in toward the sun, which means it's going to accelerate. So we have to do a lot of fancy things, flybys with Earth to slow it down, get it in the right place at the right time. It's actually 2 spacecraft. One of them is called the Mercury Planetary Orbiter, and the other one's MEO, which I can't remember what it stands for. It's going to study the magnetic field of Mercury. Mercury, like Earth, has a magnetic field. Some of these other planets don't. Venus might have a weak one. Jupiter and Saturn obviously do. They've got aurora. But they're also going to study, they're going to study this magnetic field, and they're going to verify Einstein's theory of general relativity by measuring parameters in the Newtonian physics of this whole thing. Because Mercury is closer to the sun's gravity well, there's going to be relativistic effects, minor, but the instruments on board are sensitive enough to measure these things. Pretty cool stuff. Another NASA mission was given the green light to do some research. Are you working on this mission?
I just did artwork for it. No, I'm not on this.
This one's called Lucy, and it's going to study the Trojan asteroids near Jupiter. There's a group of asteroids that kind of move with Jupiter, and they're called the Trojans. They're going to study, hopefully we'll find out a bit more about the beginning of the solar system. These are exciting. Dan's going to tell us more about this stuff, but it's going to be exciting stuff. This is my favorite science topic of all time. You guys know this. Oumuamua. This was the Oumuamua. It's a Hawaiian word for visitor. roughly. This thing, we detected it last year, a quarter of an astronomical unit from the sun. We found it, but when it was moving away from us, we didn't even see it coming. But this thing is on a hyperbolic orbit. It's not from our solar system. These two guys, so some of the interesting things about this is they think it's a comet, but it didn't have any outgassing. But then we noticed it was accelerating away from the sun. It should be slowing down, right? Because if I, just like a slingshot, if I come around a heavy Earth or something like that, or the sun, I'm going away from it. I speed up as I go, and I slow down as I go back out. This thing is actually speeding up as it's going, leaving, which is weird. One of the ideas is that it actually is a comet, and it's being pushed along by its outgassing. But these two, trying to get their names, they have a new study. It's called "Could Solar Radiation Pressure Explain Oumuamua's Peculiar Acceleration?" They're actually proposing that this could be a fancy light sail. A light sail, we usually know is that kind of big square, thin, mylar type thing. But they're suggesting that maybe there's something to be said for its shape and the way it is, just a different idea. The study was published, if you're interested, in the, where was it published? If you look up these two guys, Shmuel Yali and Abraham Lieb, it's in anyway, if you look them up, if you look this idea, if you'll be able to read the whole paper, it was pretty fascinating stuff. I could spend all day on it. I just think it's the most exciting thing. Voyager 1 is in interstellar space. It crossed what's called the heliopause that last year, but now we're getting indications from Voyager 2 that it's coming close to encountering that same. Voyager 2 was launched first back in 1977. Voyager 2 was launched first, and it encountered Jupiter and Saturn, went on to Uranus and Neptune. Voyager 1 was launched second, but in 1977, like a couple weeks later, and it just encountered Jupiter and Saturn, and then shot up north out of the ecliptic, and they're going in different directions. So Voyager 1's heading up, and Voyager 2's heading down. But what we're looking at are these numbers right here. You'll see this is Voyager 1. This was, I took the screenshot this afternoon. It's wrong. Because is constantly moving. They're moving, right, at high velocity. 38,000 miles per hour. That's pretty fast. This one's moving much faster, 4,000 miles. Anyway, we're looking at these numbers here. This is these are the molecules from the sun. These are molecules, cosmic ray molecules. There's a few instruments that are ticking away on Voyager, and you'll see on Voyager 2, it's still up in the 25, 26 range, but they've been seeing fluctuations exactly like what they saw in Voyager 1. And so they think that it's now moving out of this, out of the heliopause, encountering the heliopause. But just because it's out of the heliopause doesn't mean it's anywhere near anything else. In 300 years or so, it's going to encounter what's called the Ur cloud. This is the hypothetical cloud of icy bodies that we're starting to encounter with New Horizons. But in 300 years, it'll encounter these objects. Objects New Horizons encountering are called the Kuiper Belt objects. And then in 30,000 years, it'll actually be closer to another star than it is to the sun. When it crosses within 1.6 light years of a star called GJ 445, which is in the constellation of Camelopardalis, if you want to go out and look it up. You might be able to, that's 30,000 years from us. All right. Astronomers this month found the Milky Way's youngest known pulsar. This is a Chandra Space Telescope image. This is exciting because, so the blue region represents high energy X-rays, and the purple region shows lower energy X-rays. So the Chandra's an X-ray telescope, so Hubble sees in visible light near infrared. Chandra's looking at a completely different part of the spectrum. Sometimes they put these images together and they're really spectacular. Of the 2,000 pulsars, we only found these pulsars like in 1967, so we found 2,000 of these things. What's cool about them is that they help us determine distances in the universe and stuff. So finding this one's kind of neat. Of all another thing this month was in the monthly notes of the Royal Astronomical Society, the Gaia Satellite, using data from that, these astronomers found that they were looking at, they were trying to find stars that are zipping out of the galaxy. Well, what they found was a bunch of stars that are moving through the galaxy, like from outside. Pretty cool. Completely different than what they were expecting to find. So that's why I find these things exciting. Scientists confirmed that there is indeed a supermassive black hole in the middle of our galaxy. This is kind of cool because they found that there was this, where's my notes? They were using ESO's Very Large Telescope array down in South America. And so in this accretion disk, they found some things moving at like 30% the speed of light, which was is predicted by Einstein's theory of general relativity. So they're pretty sure that there actually is this supermassive black hole. Back in 1987, we saw the brightest supernova that humans have ever seen. It's in the Large Magellan Cloud. It's far away. This is a GIF animation of it changing, expanding over time for the past 20 years. Pretty neat. I thought I'd include it. Out of the weirdest, not weirdest, but the scariest sighting stories that I ever ran across was this thing this week. It was in the World Wildlife Federation or Fund made this study. This has nothing to do with astronomy, but it has everything to do with science and Earth. But apparently, since 1970, we've wiped humans, single-handedly wiped out 60% of the vertebrate life on the planet. 83% since the dawn of civilization. This is I mean, it's got a pretty wide margin of error. That's what that yellow is. But I thought I'd bring it to your attention because this one, I was like, look, how come this is not like on front page news? It really isn't. I'm going to show off. I get to do the cool stuff. I work for the National Solar Observatory. I got to create that sun this week using imagery from our. We have 6 observatories around the planet taking imagery of the sun all the time. Now this is not real. This part's real. These are real filaments, prominences coming up off the sun. But this other stuff I put in, I call it the angry sun, active sun. But this is a real image of the sun that we got this week. Or it was released by one of our scientists anyway. We took it from the Dunn Solar Telescope. Now you might remember the Dunn as being the telescope that was shut down last month because of an FBI investigation. Yeah, that thing. So we took this image, and I got to colorize it. That's the real edge of the sun. Isn't that so neat? I just think this is the coolest image. This one's neat too with this sunspot. But this is an example of what we'll get. We're building the world's largest solar telescope on Haleakala in Hawaii. And it's we're going to get this type of stuff. So pay attention. It's going to be cool. Just like he says. Cool. I just have to show off. I created that. I walk away. Sure.
There's so many things I can say about Dan. Asteroid expert. And, you might have seen my email or the article in the Mountain Messenger about him. But some of the really interesting, he creates these beautiful space songs. And in the mountain, look at that, it's just so beautiful. All sorts of different things. But he's one of my favorite space artists, and there are a whole bunch of them actually out there. He also is a bird lover, and has traveled, what do you say, like 3 times in this last year,
Just
but
last year, yeah, 3 times
yeah.
in South America in the last year alone.
just to look at birds, you know, take their pictures. And he's also underwater cave diver and rescue, and a pilot. Yeah, how many planes have you flown? Different types?
Can't remember.
15?
Okay, what's the coolest?
The coolest plane?
The Hornet was the most fun, I think.
Just the F-18.
Yeah, just the F-18.
And, let's see, what else do you want to say, or do you want just people to know?
Just all around good guy. That's what-
Yeah. Just damn Dirta.
Thank you, Barb, and thanks for having me back up. I think it was maybe 5 years ago last time I was here. I know a couple of you, I recognize a few faces that were up here at the time. Don't remember what I talked about 5 years ago, but
Yeah.
I don't remember what I had for breakfast this morning either. Barb asked me to come up and what would you like to talk about? And quite frankly, I scratched my head for a while because there's so many things that I've been doing that I could have probably had some fun talking about. I decided not to choose and thought I would just do a little compendium of 3 different random projects that I'm working on at the moment, and thought I'd give you a little tour of that. And so for the next 3 hours, we'll have, it'll go faster than that, I promise. Actually, so seriously, there are these 3 various things I've been working on, all related one way or another to asteroids, or at least small bodies in the solar system. It's what I do, it's what I'm most interested in doing. I've been fascinated with asteroids since graduate school. Not forever, actually. What got me into astronomy in the first place was extrasolar planets and Kepler and the kind of things that are going on right now with that. If I'd have stayed interested in that stuff from an undergrad into grad school, I probably would have been working on Kepler data and things like that right now. But since grad school, it's been all asteroids all the time, making molehills out of mountains, I like to say, because most of my research involves collisions and impacts, and the things that break asteroids apart. Impacts are probably the dominant process that affect the lives of the asteroids, and it's also darn fun to just go out there and shoot things and blow things up. So that's what I focus my research on for that reason. I think one of these might be a pointer, but they probably don't need a pointer on a little screen like this. So,
You won't show, I'm sorry, man, you won't
yeah.
show.
So I'll just walk over and point. We'll do it that way. I want to talk about a set of impact experiments that I've been working on with some colleagues from our San Antonio headquarters of Southwest Research. I'll talk a little bit about mapping ejecta blocks out at Meteor Crater, probably one of the best preserved impact craters on our planet that you can go and readily visit and see what the effects of one of these impacts are like on the Earth. And then just very briefly at the end, we'll get a little tour of a bit of zero gravity experiment stuff that I'll be actually doing in just about a week from this coming Tuesday. I'll be up on an aircraft doing parabolic flights and more microgravity experiments, so we'll talk about that a little bit too. So this first one has to do with basically protecting our planet from basically the one natural disaster that we humans can actually do something about. Can't do much about earthquakes, and really can't do much about hurricanes. We can't change them, and all we can do is react to them. The threat of an impact by a small asteroid is actually something we think we can start to get a handle on actually doing something about, and not just letting it happen. One of the more, so the idea being, okay, the dinosaur, to quote the famous quote, basically, right, the dinosaurs went extinct because they didn't have a space program. We know 65 million years ago, there was an impact by a very large near-Earth asteroid, right? This is something 65 million years ago, about a 10-kilometer diameter object striking the Earth in what's now the Yucatan Peninsula of Mexico. Basically, imagine Mount Everest slamming out of the sky onto the planet. Very, very bad day environmentally for the entire planet, and that's something we would like to not have happen again. Fortunately, because of witnessing the rain of cometary fragments on Jupiter back in 1994, Congress woke up to the idea that, my gosh, impacts actually can happen out there in the solar system, and they can happen today. We finally got going this wonderful survey of the potential impactors in our neighborhood of the solar system. And in the couple decades since then, we've actually done a pretty darn good job of surveying for the sort of the species ending, civilization ending scale near-Earth asteroids that are out there. I don't know about you, Clark. I don't lose any sleep about these things these days. Back then, 20 years ago, it was kind of an unknown problem. There's all these potential objects out there. We don't know where most of them are. One can pop out of the blue and and cause some problems for us. Today, we've surveyed the vast majority, not all of them, but the vast majority of the big guys that are out there, these civilization enders sort of things. But there are still many, 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 many thousands, millions of smaller scale objects that, while not necessarily bad for the planet on the whole, can be very bad for your city if it happens to come raining down on top of you. A few years ago we saw what happened in Russia, in Chelyabinsk, when an object, not that big, about the size of this building or so, maybe a little bit larger. Well, actually, maybe not. About the size of this building came raining down and caused enough, the detonation in the atmosphere was powerful enough to blow out windows and actually blow down a few walls of buildings and so on. A lot of people had their faces cut by the broken glass. They heard the boom, the sonic, they saw the flash of light in the sky. This is the pre-dawn, morning twilight Russia, the equivalent of rush hour traffic there in Chelyabinsk. People saw the flash. They went to the windows to see this cloud of debris in the sky, and of course, shockwave from the boom in the atmosphere came. So as everybody goes to the windows to look out, the windows come shattering in, and a lot of people got their faces cut and some other injuries like that. That's the scale of sort of asteroid impact that we can actually do something about, because that's an object that's small enough. If we have warning time that something like this is out there and going to be striking us, if it's a bad enough sort of if the circumstances of the impact are bad enough, it's something you might want to choose to go and prevent from happening. And probably, and there's a lot of sci-fi-ish ideas of how you might do this sort of thing. You can shoot it with sharks with laser beams on their head, right? And there's all these fancy ways of doing these things, right? No, seriously, there are sort of ways of causing the surface of the asteroid to vaporize in some way, so that almost like the way that the jetting of a comet will naturally push on it a little bit and cause more than just gravity to affect its motion in the solar system. If we can somehow heat up the surface locally of a small asteroid, that local jetting, the evaporation of volatiles, the water that actually exists in the mineral structure of many asteroids, comes jetting out, and you can actually push the asteroid off course that way. You could do it with a laser. You could do it with particle beams. You could do it by focusing sunlight on the object. There are a lot of physically plausible ways of adjusting the course of an object like this out there if you've got enough time to do it. Not all of them are necessarily all that technologically practical at the current time. But one of them that is something we've actually done before with the Deep Impact mission, which was a mission to go and actually impact the surface of a comet from a scientific point of view, because we wanted to make an artificial crater and expose some of the interior material of that comet nucleus and understand what that's made out of. It gave us the practice of actually targeting a spacecraft into the oncoming nucleus of a comet. That is a technique that we could actually use to use the kinetic impact of a spacecraft onto a small asteroid to help adjust its course, push it out of the way. And so this, what's called the kinetic kill technique of pushing an asteroid around, is something we can actually do. The basic idea here is, I'll put the mathematics up for you if you care to worry about the equation, but basically all that's happening is it's the momentum change you get from running the spacecraft into the asteroid, okay? But it's not just the momentum change from the spacecraft hitting the asteroid. When you do that, you make a cratering impact. These are very high-speed impacts. This is not just crashing a car into a building at 60 miles an hour. This is slamming a spacecraft into an object at 10 kilometers per second. Okay, what's that? That's probably on the order of 20,000, 22,000 miles per hour, something like that. These are hyper-velocity impacts. These are impacts that are faster than the speed of sound in a rock. Okay, and when you do that, the surface of the object reacts rather explosively. The ejecta that comes spraying off flies off at very, very high speed. And so you ran the spacecraft into the object, the ejecta, all that cratering debris that now gets blown out into space this way, there's not a lot of it, there's not necessarily a great mass of it, but it's moving so fast, there's a lot of momentum that's carried away from that, from the asteroid by that ejecta. And conservation of momentum, you're carrying all that away, there's a pushback on the asteroid from that as well. So there's a multiplication factor of not just the momentum from the spacecraft, you get some added momentum from all that ejecta spraying off. Okay, and that works to your advantage. And we know this happens, I mean, you can measure it in the laboratory. The problem is we don't actually know very well how that scales with size. We do this in the laboratory, or we can calculate what it should be, but we don't, I mean, other than this one experiment we did running into a comet, but not for the purpose of this kind of an experiment, we've never actually measured what this would be for a real asteroid. We think we can kind of calculate it, but until we actually go out there and do the experiments, we don't really know. We can do these experiments in the lab, usually at small scales. You take a rocky target about the size of your fist, and you shoot a BB into it, and you can make these measurements very nicely. But then extrapolating that answer up to something the size of, you know, a small city is a different story. And so what, did that movie actually run while I was talking? What we've been doing is trying to help scale up these experiments a little bit. Not just kind of guessing what they might be, writing out the equations, which take a lot of, I mean, there's nothing wrong with writing equations, it's just, there's a lot of assumptions that go into those calculations, assumptions about what the surface is going to behave like. And so one way to help bridge the gap between our small scale experiments and those calculations that predict how a small, you know, something the size of Wonderview is going to behave, is to do those physical experiments at a big scale, okay, kind of in between. It's a lot easier to try to extrapolate the answer that way when you have another set of data points that are just a little bit bigger out. And so what we've been doing, and I say we, this is our satellite, our parent office of Southwest Research down in San Antonio, Texas. James Walker and his group down there, we have some pretty big impact experiment facilities down there. We have big guns, big cannons that we can use down there. And we've been shooting very large scale targets, not just fist-sized rocks. How many of you have been down to the 29th Street Mall on Pearl Street? You walk around the outdoor thing there. Have you seen the big, large, black granite spherical earth that floats on the water, right? You've probably seen these water bubbles up in the summertime, and you can sit there and you can spin the globe around, right? I got the bright idea a couple of years ago that, you know, there's a company out there someplace that makes these big, round, spherical rocks. I wonder if I can get them to let me shoot one of them. And so well, you know, we had some other experiments we were doing, but it's like, where do you go to get a big rock target like that? You go to the place that makes these big round rocks for the water features. And so I called up the company in California that does these things, or one of the companies that does it, but they're the kind of the most well-known. I said, you know, I'd like to buy, you know, get a big, you know, meter, you know, 3.5 foot diameter piece of granite from you, a nice big round one. Why round? Because most of the targets we shoot are round, because the mathematics for double checking how the experiments work and then trying to extrapolate and predict really work well with round things, okay? So can I get one of these round granite spherical things? Like, sure, happy to. But you know, of course, I'm thinking, okay, now the bad news. How much is this going to cost me? How much is this going to cost my NASA grant, right? It turned out to be a rather pleasant surprise. I'll tell you the answer. The answer is I got 2 1-meter diameter granite spheres. They were quarried out of a face of rock in China. They were milled down by hand to roughly spherical things, and then polished off into these beautiful, perfectly spherical big balls of granite, stuck on a ship across the Pacific to California, and then trucked from California to Texas, where we did the experiments, 2 of those, for a grand total of $6,000. So that was a great amount. I mean, that was efficient use of taxpayer money. We got some good data out of it. I'm going to skip the mathematics of this. There's a number called beta. Beta is this this measure of this ratio of how much more momentum do you get out of the ejecta spraying out than you got out of just the thing striking in the first place. And the answer comes out for our granite spheres. It turns out that we got about twice as much momentum spraying out from the ejecta than we got just from the big golf ball sized projectile striking it in the first place. And that's rather interesting because that's kind of right on par with what some of the numerical calculations were suggesting for rock of that type. Those same kinds of calculations suggest that when you scale up the speed to even faster stuff that's like the spacecraft is going to run into these things, and you scale up the sizes to some of the asteroids, that we might get as much as 10 times or more of the momentum enhancement just from the ejecta spraying off. That's good news. That means that it's a big help for us if we want to slam our spacecraft in and push the asteroid around. We're going to actually test this. NASA has a mission, a portion of a mission that was going to be a dual, United States and European Space Agency mission. It's now just the NASA side of it called DART, the Double Asteroid Redirect Test. The idea is, okay, the numerical calculations are fine, doing these fancy big-scale experiments is fine, but let's go out there and do the real thing. Let's take a real spacecraft and slam it into a small asteroid and watch the change in how it moves. And the best way they can think to do this, the most obvious way to measure the change in the speed of the thing that you're hitting is, let's not just take a lone single asteroid out there in space. Let's actually run into the small moon of a small near-Earth asteroid. And it turns out to be much easier to watch the change in the orbital period of that moon around the primary, in a binary system like that after you whack it. And so what the DART mission is going to do is run into the moon of a small near-Earth asteroid. That's the idea, at least. And so these experiments that we've been doing are in support of the DART mission. Here's one of our cannons down in San Antonio, Texas. This is what one of our projectiles looks like. This is a centimeter scale here, but I'll tell you right now, that's the size of a golf ball. It's a big aluminum golf ball. And we can fire it out of our cannon at speeds of up to about 2 kilometers per second. That's pretty darn fast and pretty energetic. Not quite as fast as the spacecraft are going to be running into, but still fast enough that get us into this regime where it's an interesting experiment to do. We've been supplementing those big scale ones with continued experiments at the NASA Ames Vertical Gun Range, the AVGR. You've probably seen this on TV. This is that gun in California that shoots, I didn't put a picture of the AVGR up there, but you've probably seen this on TV. We basically fire little glass and steel BBs, literally BBs at about 1/4 inch scale, 1/8 inch scale, at speeds up to 5 and 6 kilometers per second. But because it's a smaller projectile, we use smaller targets. So here we're shooting fist-sized stuff again. But again, it's helpful, and we're shooting artificial asteroids, plaster sand, very porous, pumice, very porous. There's a new mission going off to an asteroid called Psyche, which is a big piece of stainless steel out there in the main asteroid belt. So we've been doing some shots into nickel iron as well, actual meteorite samples too, to see how metal asteroids might be affected by these kinds of things. Again, big scale experiments. You get literally a truckload of pumice that comes on pallets. These are big chunks of pumice. I mean, the world's biggest foot things, I guess. And it's a little bit harder working with stuff like this because now you're not just hanging a piece of rock from a string in your laboratory chamber. You need forklifts and chains, and I like doing big scale experiments. It's kind of fun. We put lots of high-speed cameras around because all this happens very fast. What we're looking for, what we're actually measuring, you'll see our targets. There's a little fiducial target on the side of our target, so you put a little black and white checkered, optical target on it, so you can measure very precisely in the high-speed video. After the flash of the impact, you can then watch the recoil of that mass of rock that we're shooting. We've measured the mass of the piece of rock we're shooting. We know the mass and the speed, and therefore the momentum of the projectile that we're shooting. So we know the momentum coming out. We know the mass, and we've measured the speed. Let's see if I can. Oh, man.
We tested it.
Yeah, we tested. Well, okay, let me do the next one if that does the same thing. I think what's happening is, okay, there you go, boom, okay, now finally we get to see the beginning part of the experiment. This one was shot a little bit faster and a little harder. This is a little bit more than just a cratering experiment. You can actually see the piece of pumice cracking back there. We wrap it in chicken wire, just in case it does just this. Actually, it tends to want to fragment more than just crater. You go to the next one, I might show that one from the side. Yeah, here we go. Projectile coming in, boom. Right, you see the cracks propagating through the target. What you don't see too well here, but it has to play out longer, that's our optical target that we're watching. If I had to put my finger on the target at the beginning, let me do it this way. You can kind of see it rocking back ever so slowly. I'm keeping my finger in the same spot. Right, that's that momentum that we're measuring. I've got other video here, I think, at some point to show you, but there's what the aftermath looks like. So this is one of these pretty large-scale cratering things, but you know, this is what one of those actual real asteroids might do. It might actually crater and crack a little bit. That's kind of part of what we want to know, right? That's, I mean, you know, some of these asteroids are rubble piles. They're just chunks of rock, like Ryugu, the one that that Hayabusa 2 is arrived at. Bennu, which OSIRIS-REx is just arriving at, are probably rubble piles. These are just, you know, highly fractured, highly shattered shards of rock out there that are just barely held together by their very feeble gravity. And so they may not act like a solid brick when you hit it, they may act more like a sandbag. And the difference between how those, you know, react is going to be very important.
What's the percentage of those kind of rubble pile asteroids versus
Yeah, big
Psyche's
solid.
going to iron?
Yeah, going to an
you
iron
know,
thing,
I mean,
right.
You know, what's the, you know, what's the mix?
It probably depends on what size you're looking at. Biggest asteroids are probably too small to be effectively, you know, they kind of re-heal themselves, if you will.
Yeah.
If you get down in the sort of middle size range of asteroids, the things that are, you know, a kilometer across, 10 kilometers across, there's probably a high fraction of those that are rubble piles.
Yeah.
And then you get very much smaller things, you know, the size of this room, they're probably too small to be rubble piles, and they're probably being back to, you know, solid monoliths of something, or semi-solid monoliths of something. So I think there's a good probability. I mean, you look at Ryugu and you look at Bennu. There's two of these near-Earth asteroids that we're visiting right now, and both of them appear to be rubble piles.
Yeah.
Itakawa, which was visited by the Hayabusa 1 spacecraft, appears to be a rubble pile. There's circumstantial evidence for a lot of these objects in the near-Earth population, in that size range, that sort of, you know, kilometer and, you know, a few kilometers across. There's lots of circumstantial evidence that a lot of them, most of them.
So Earth impactors, let's say an asteroid coming in, is there a greater chance that it's a rubble pile, or it's something more solid, or is it? I mean, what?
Yes.
Should we be worried about?
I mean, seriously, we don't know. I mean,
Yeah.
there's a good chance they can be a rubble pile. There are, you know, there's several percent, 7%-ish or so are solid nickel iron things, the thing that formed meteor crater.
Last longer.
Well, you know, you get more wham for the size in a nickel iron object. One, it's more massive for its size, it's denser, and two, it's going to be a substantial solid object. You know, had the impactor that formed meteor crater been a rocky object, the same size, and not a nickel iron one of that size, it probably wouldn't have made it to the surface to make a crater. It would have detonated in the atmosphere like Chelyabinsk.
Yeah.
Okay, so it's,
Okay.
you know, there's an example. Papers are being written. Okay, we're doing the experiments. It's fun stuff. Okay, just so I don't actually do 3 hours worth of stuff. Speaking of meteor crater, absolutely, if you've never been there, absolutely fascinating place. Like I said, probably one of the best places on the planet to go and actually get a real visceral sense of what an impact of something, you know, of this sort of scale actually is like on the planet. I should have brought one of my movies of an explosion experiment I did that was like a little you know, 20th scale meteor crater. One of my things I like to do is blow things up. So I do a lot of television work, and so one of the National Geographic came to me once asking about, you know, talking about, is there a way we can illustrate the power, the immensity of the impact of the KT impact, the KPG impact now, the dinosaur killing impact, and can can we make a big impact? And it's like, so that's kind of hard to do, but big explosions, if you put the explosive charge at the right depth below the surface of the rock, it mimics the excavation flow of an actual impact. And they liked that idea. They said, we'll bring a lot of money. How big an explosion can we make? So we set this up, and I set up pallets and pallets and pallets of explosives out in the desert in New Mexico. We had 5,000 pounds of ammonium nitrate fuel oil mix, and made a crater about 55 feet across and 12 feet deep, and it was pretty impressive. But it was like a little miniature meteor crater. It was really beautiful. What's really cool about impacts like this is that it's not just the crater itself that's of interest to us from the perspective of teaching us about the impact physics and the subsurface geology of places like the moon, for instance, where you're seeing these craters. It's also the ejecta out around. It's all the stuff thrown out of the crater that leaves clues to the physics. And what's going on here, something interesting is going on in this impact that has created a very asymmetric ejecta field. You're looking at all the debris thrown out of the crater, and the finer scale stuff falls back across the surface, and on the airless surface of the moon, that material regardens the surface of the moon as it lands and brightens up the surface, and here it's very asymmetric. There's a big gap coming out of the middle of it. The answer at the back of the book is that this was an oblique impact. This was not some, the sort of impacts can happen from all angles from the vertical. The asteroids don't know anything about the fact that the Earth is there or the moon is there until they hit. And so they can come in just glancing the surface, they can come in straight down, any angle in between. Statistically, you average it all over, the most likely thing to expect is an impact at about 45 degrees or so. But these are not impacts like just throwing a rock onto the surface of the ground. Remember, these are hypervelocity impacts. The impact energy is released in a shock. It's a sonic boom in the rock, if you will. Okay, and so it almost doesn't matter what direction the impactor comes in. That excavation flow that creates that crater is going to make pretty much a nice, hemispheric, circular sort of crater. Unless you get to pretty oblique. And then you actually do start to see the shape of the crater get a little bit more elongated, and you see that ejecta spray be more directed downrange and leave things like gaps like this. Barb, I'm sorry, you
Yeah, so the meteor crater in Arizona, the meteor crater, how did that come in? Did it come straight?
We don't know. We don't know, actually. It's frustrating because it's probably one of the best studied impact craters here on the planet, and yet we don't know. I'm not saying we have no idea. There are some hints and some clues, but I'll tell you that those same hints and clues have led some researchers to say it came in from this direction. The exact same hints and clues are interpreted by other researchers to say it came from that direction. Okay? Part of the problem is it's a little confusing. It's a little hard to completely
Because
understand.
erosional factors?
No, we're just still learning about the physics of how it actually translates into how the rock is excavated. It's a little confusing at meteor craters. Not just a perfect thing. The crater walls aren't exactly beautifully, perfectly symmetrically ripped up. There's a pre-existing joint structure in the rock layer cake out there in northern Arizona that has affected the way the crater has formed.
Yeah.
In fact, if you here's a LiDAR image of meteor crater, aerial LiDAR that has been converted into a sort of a topographic image, if you will. And you can see this really interesting feature of meteor crater, which is it almost looks more squarish than perfectly round. And that's a artifact of this pre-existing set of cracks and joints in the surface rock. It means that there is a place at the corners where it's more likely for the walls to rip out along those joints, and so that's what's led to the square nature of the crater. And so that's what helps confuse.
Why would they look at that and go, it came in straight on?
Because the energy released is so great that shock wave that's again supersonic in the rock shock wave that propagates away doesn't care what direction it came in from. It's so energetic and so fast,
Huh.
it expands spherically almost no matter what direction you've come in from.
Okay.
Unless you get very oblique, then you start to see hints. Okay, anyway, so meteor crater's been well studied. Gene Shoemaker, the godfather of this field in terrestrial impact cratering, was one of the people most responsible for really elucidating everything we know about the impact nature of this feature. But strangely, one thing that's actually never been done yet for meteor crater, in all these years of study, is to systematically map out. This just shows you the quality of the LiDAR data. You can actually see the cars in the visitor center parking lot in the LiDAR data. But you can also see things like these big chunks of rock and ejecta out on the flanks of the crater. Nobody's actually ever, we've done it for craters around the moon and on Mars and many other places in the solar system, systematically mapped out the size and spatial distribution of those blocks around the crater, because they hold clues as to where all that ejecta went and how the actual physics of the outcome of the crater. But nobody's actually ever systematically done it for meteor crater, believe it or not. And so, working with my colleague Dave Kring at the Lunar and Planetary Institute in Houston, we decided to actually go to these types of images and let's start actually mapping out all these things around the crater. His idea originally was to take this really cool set of LiDAR data. Now you're looking at the south rim of the crater. Here's the rim of the crater, the interior, the exterior. And again, all these little lumpy things that are out here. And let's just start counting them all. How big are they and where are they? And so I started studying into this and I'm thinking, well, I've been to Meteor Crater and I know what it's like out there. It's not just rocks all around the rim of the crater. There's a lot of pine trees out there as well. And how many of these bumps out there that we're seeing in the LiDAR data are actually trees and not rocks? So I'd better go to the Google Earth imagery itself and see if I can line things up and see if I can pick out and use the Google Earth images to tell me, okay, is that really a tree or a rock? Or let me do that. So see if this plays. Yeah, so I'm going to bounce back and forth between LiDAR, Google Earth, LiDAR, Google Earth, and of course it's stick half of it. But the key is, it turns out that around that south rim, almost every bump you saw was actually a tree and not a rock. And so I decided, you know what? Let's just skip the LiDAR data altogether. Let me make a really high-res Google Earth map around the entire crater, and just use the imagery itself and just count the blocks from the imagery. So here's a kind of an overview of an actual Google Earth image now, looking down in the crater. I had to define my search area, and so we picked the very center of the crater. In fact, the center of the one mine shaft in the very center of the crater, because people have used that in the past in the literature, so we decided let's just use the same central point. Let me go out there and count every rock that I can see from the imagery in this 2 kilometer radius region out from the center of the crater around the entire crater. And then wake up in a horror the next day and think, why did I decide to do this? Because there's a lot of rocks out there in the desert. And so I'm skipping through to kind of you can kind of see a bunch of dots out here. These are my first cut at mapping out some of the bigger ones. We can actually compare the size distribution of those rocks basically out there to size distribution of rocks around lunar craters. Guess what? Looks pretty similar. Shifted in size because we're looking at different size craters, but similar sort of thing going on there. I'm going to zoom in because it's really hard to see what's going on here. But if I zoom in, you'll see the comparison of what I've been doing. Here's just one tiny little postage stamp area around the rim of the crater. This gap right here actually defines where the eastern rim of the crater is. So everything in here is interior of the crater, and then out this way is out in the exterior where all the ejecta went, basically. Every one of these little dots is a place where I've marked a boulder. In my quick look at the LiDAR data, I went back to the Google Earth thing and said, well, I can see a lot more rocks in the Google Earth data. And started actually, and not only can I see the rocks, I can see their shapes as well. And so I just sit there with my light pen on my tablet and just start drawing out where every place I see a rock, just outline it and do it and just keep going and sit there day after day and pull your hair out. And then thousands and thousands and thousands and thousands and thousands of blocks around Meteor Crater. And we're up to, you know, it's I don't know, 100 and something thousand rocks now or something like that. The answer is basically I can very reliably measure not only the locations but the actual size and the shapes of just about every rock around Meteor Crater, about down to the size of about this, you know, laptop, about the size of a good sized dinner plate. And so that's what I'm still in the process of doing, and I probably will be for the rest of my entire life. Measuring these things out. So yeah, I just create this big table of every rock I measure, where it is, latitude and longitude around the crater, basically how big it is in pixels and what its major and semi-major axes are and all that kind of fun stuff. And you create this, you know, here's just the northeast quadrant of the crater. I'm down in here mapping now. This was last summer doing this. You can see where the rim of the crater is out this way. The visitor center parking lot is right over here, so there's a big gap right in the distribution here. And you can start doing things like, you know, measuring the size distribution and the number of boulders in all of these various little sectors out here. And you know, there's a lot more craters over here, or a lot more boulders over here, and this is the kind of stuff that rock geology, planetary scientist people really enjoy a lot, okay? And the value of this, seriously, is that we can compare it to other craters that we've measured on things like the moon. And is that telling us anything new about the subsurface structure of the layer cake of rock there at Meteor Crater and so on? So here I'm looking at, you know, size distributions, cumulative size distributions. This is, you know, how many rocks are there bigger than a certain size out there around the crater. And the slopes of these things tell you things about the behavior, and it's data, folks. Yeah, more data. Just to give you an idea, okay? So this is one of the smaller of the rocks that I can see in my Google Earth imagery. You might just see here a little black line, which is actually a big broomstick that I taped two white tape markers on, exactly 1 meter apart on the broomstick. That's my standard scale, so I can set the image scale, so I know exactly how to convert the pixels that I'm seeing in an image into an actual physical dimension of a rock. That, you know, these are sort of the smaller things I'm seeing in a Meteor Crater image. This is an aerial image taken by other means, right there, local at Meteor Crater, and you can actually use this, map out all the rocks in that image, and then use that to tell me in this one little tiny little test section, extrapolate down now, what am I missing in the Google Earth imagery? Okay? And push that down to even smaller sizes. And so here's an example. Here in that area is what I can measure with Google Earth imagery, but then if I use that close-in aerial imagery, I can push that information even further down in that little test spot area and give me some insights into what might be happening all around the crater as well. So that's how these kinds of field studies go. Dave and I are still doing this work. We'll probably be out there again next April or May to go out and do some, you know, like in the field spot checks. So I can see what I'm seeing on my images from Google Earth, but let's go there and actually physically walk around and say, okay, I've mapped this boulder. What am I missing down here at this sort of scale now, literally, so I can kind of help interpret all that. Now, you know, Meteor Crater happened 50,000 years ago, approximately, and it's still claiming casualties, because 2 years ago when I was out there doing one of these spot checks, it's a very windy place out there at Meteor Crater. If you ever visit the visitor center, they actually sell t-shirts at the visitor center that say, I survived the winds at Meteor Crater. It can be very, very windy out there. I don't have a particularly high mass to surface area ratio, and I happen to be out there standing on top of one of the big ejecta blocks getting images with my camera out there 2 years ago doing some of these spot checks, and a gust of wind blew me off the crater and blew me off the rock, and I ended up mangling up my right knee so badly I had to have surgery to reconstruct it all. So it's still claiming casualties.
But Dan, I want you to tell them, you were judicious in doing your therapy.
Oh yeah, if this ever happens to you, if you ever tear your ACL,
Call
and have
Dan.
to, yeah, and you have to have surgery to recon. Do every single bit of the physical therapy that your doctor tells you to do it religiously, and you will get back to normal. So that's
how
nice.
many hours a day was that?
It consumed basing on making sure I got my knee back.
Was so like 4 hours?
Yeah, I spent about 4 hours a day. Yeah.
Yeah.
Because I want to go out.
I wanna
I want to be able to go out and map more blocks, right? So okay, so last little bit. This is going to go fast because I'm actually going to break out of this and let some of the movies do the talking on this one. Gosh, 15 years ago, 17 years ago, something like that. One of my astronaut friends, Don Pettit, was up on the space station, Expedition 7. We're in what, Expedition like 24 or 26 now or something like this. This is way early on in station history. Don is a genius. He's just an amazing guy, and in his spare time up there, literally on Saturday mornings, he would have some personal time on the station. Everybody needs a break. Even the astronauts get a break. They get a little vacation every day, a bit of a day off. Don, on his days off, wouldn't just go and float and look out the window. He actually still did work on those days. He did something called Saturday morning science. He knows that people like us are fascinated by watching the way stuff behaves in zero-G. It's this very alien sort of environment for most of us. And so he would be playing with various things and filming it. And with not just playing with it, but playing with it from the perspective of what is this teaching me about some basic physics. He would do things like mixing fluids together and watching other interfaces do things. Well, the astronauts get their food in basically prepackaged plastic bags. Even the salt and pepper and sugar and things that they use for seasoning come in sealed plastic bags. What Don did was to take a little bit of air and poof it into one of the bags that had some of the salt and some of the sugar and some of the coffee grounds and things like that. And he would shake them up in front of the camera, and some fun things were happening, which I think is the movie I want to break out of and show you now. And hopefully the audio will play and all that kind of stuff. Now, how do I minimize? Oh, I'm going to minimize that. And minimize that. Oh my gosh, gotta minimize everything. I gotta get to the directory where my things were, or I can just go down here if I could do it faster. Well, I'm not used to touch screen. I'm still living in the old days. Which is faster. Yeah, I know. But I'm on Luddite. I'm here for it. Let's see if the audio plays.
Particle agglomeration.
I'm just gonna let Don do
We
the
have
talk.
a gallon-sized plastic bag filled with 1 millimeter diameter sodium chloride crystals.
Salt.
You shake this up, and the individual crystals will rapidly form agglomerates, and these in turn form floccules of the order of several centimeters on the side, and all of this happens in about 10 seconds. Here is a slow motion view of the same thing, showing the individual crystals rapidly forming agglomerates, and again these form floccules, all within about 10 seconds.
I'm gonna do one more at least.
Here we see a 2 to 3 centimeter sized agglomerate that is impacting the wall at about 1 centimeter per second, demonstrating a rather strong cohesiveness to hold together. And here we have sodium chloride crystals 4 to 10 millimeters in diameter, and these exhibit the same traits as we saw with the smaller crystals. They rapidly coalesce and form agglomerates and floccules that are several centimeters on an edge.
Okay, I think you got the idea. So, he's up there playing around doing this. It's coming back to mission control. Another one of my astronaut friends, who also happens to end up being a PhD asteroid scientist, also, Stan Love, is sitting at mission control. He is Capcom that day. The guy who's actually the only guy authorized to actually talk directly up to the station back and forth. Don's up there doing this. Stan's sitting back there at Capcom going, he's doing planetary accretion experiments, right? He doesn't even know it. This is like the first stage of planetary accretion. This is what's happening 4.5 billion years ago in the protoplanetary nebula, the disk of gas and dust that's surrounding the early forming sun, the dust grains, somehow you had to go from dust to planets. And some of the initial stages, one way or the other, no matter how you get there, some of the initial stages of that are going to be dust grains sticking together. And this is kind of a little bit of what Don was doing up there. So Stan got together with Don after they got back, spent a little extra time. They actually wrote up an actual peer-reviewed scientific paper on this. The downside is that Don didn't mean to be doing this as an actual serious scientific experiment. There probably wasn't a lot of salt and sugar and coffee floating around in the early protoplanetary nebula, but the basic physics is kind of still interesting. And so I got together with Stan and started talking about this. You know, can we carry this a little further? Can we actually start and do some of these experiments with things that are more geologically relevant, things that actually would be, the kind of mineral crystals that actually would be out there in the protoplanetary nebula? Olivine, enstatite, fragments, crushed up fragments of real meteorite. Let's actually see what these things would actually behave like. So to get a handle on what that's going to be like, I'm not going to be going to the space station anytime soon, but, I'm sorry, that was dumb of me, I just killed that same thing. And you had found a directory that, let's find this one. So, movie, yes. So I'm not going to be going to the space station, but I do know how to get microgravity conditions. I've done it a lot in the past. It's with the parabolic aircraft. These are things like the NASA's Vomit Comet, so-called, right? The NASA doesn't fly that aircraft anymore, but a commercial company called Zero G Corp flies their own aircraft. The idea basically is you get up there in the atmosphere, you fly aircraft on a roller coaster sort of trajectory. You put the aircraft into a dive, you pull about 2 Gs all through this part of the flight. You get up to the top of the roller coaster again though, you go over the top of the hill at 500 or 600 knots, and for about 20-25 seconds or so, everything in the aircraft is going ballistic. You're all floating in the aircraft. You're weightless. You're in microgravity. Okay? And I've done this a lot for other scientific stuff, but I thought, well, these things coalesced in Don's bags in only about 10 seconds. I'm going to get about 20 seconds on the aircraft. Hey, Stan, shouldn't we go and do this again with real stuff? And let's just go do it on the aircraft. And let me show you what that's like. Seeing as I have done such things in the past, I'm going to let this movie do the talking. TV show that aired on the Science Channel, BBC. Some of you may know this guy from TV.
Is to discover its power in the weightless environment of space. It's why I've come to this Air Force base, where astronauts are trained.
I'll be honest, I am pretty thrilled right now because I am about to boldly go where quite a few have gone before. Actually going into space, there were budgetary issues with that. But never mind, because we have come up with the very next best thing for our purposes. Where I'm headed is over there.
This plane offers thrill seekers something unique. It can cancel out the Earth's gravity. For me, it means I can recreate the conditions in which that elemental dust began to make a planet.
How you doing?
Hey, good to see you. Welcome aboard.
I'm ready.
Ready for a unique experience?
I don't know, I've never tried it, obviously. Let's see.
On today's flight, my chaperone is Dan Durden,
Thank you.
an expert on space dust.
All right, Richard. I think, which seat are you here?
I'm 2F. I just, given the context, having this conversation is hilarious. I should imagine all astronauts do this.
The flight attendant service on the space flights is not quite
I was wondering about that.
All
Do you have like Columbo or space food on there? I've got a window seat, but there is no window.
A lack of window
That's because within 15 minutes, we are going to experience weightlessness. And those zero-gravity conditions will allow Dan to show me a fascinating experiment. Inside this perspex box is the next step to building a planet.
We're going to simulate the way the planets formed in the very earliest days of the solar system. Instead of microscopic dust particles, I've got coffee. Ordinary coffee.
So in this little box, we're going to see exhibited what it was that brought stuff together.
Absolutely.
And so this is what kickstarts our process.
Big things have small beginnings.
So it all starts with a coffee.
It all starts with early
It's
coffee.
not my name. It does start with a coffee.
Even the solar system starts with
As
coffee.
it turns out, we shall see. Right, switch the gravity off then.
The plane is now climbing to 34,000 feet. Once there, it'll throttle back down to Earth in a steep arc, perfectly judged so that inside we're falling at the same rate as the plane drops. The result? A few moments of weightlessness.
Oh, I swear, I did slip. Oh, that's peculiar.
Oh, look at that. Beautiful. Look at it, Richard. Look at it. See, that's what I was trying to show you.
Unfortunately, I'm upside down. It's over there. Agnes, you come here to do these experiments all the time. Right, I'm going to watch, but I'm going to do it upside down. You're better at this than I am. I'm really struggling. There it is. What are we looking for? We're now weightless.
That's how our planet started.
So these clumps, what's bringing them together?
Electrostatic forces. Electrostatics clumping this coffee together.
So this is the effect. This is what starts it all off. It's hard to concentrate when I'm floating, but that's not gravity causing that clumping. I'm on the roof! No, I'm on the floor. Now gravity is coming back into play
And it's all gone.
it doesn't work.
That's why we're weightless, to see phenomena that we can't normally see when gravity's turned on.
So what's happening here? These coffee grains, like that first cosmic dust, rub together as they float. This means individual grains get either negatively or positively charged. And this static charge means they stick together. Just like the fledgling particles of the Earth formed 500 million years ago.
This is as near as we're going to get to being out there with those particles, without gravity. How cool is that? Need you to know that I did that only because it was the best way of demonstrating the essential principle in building a planet, and not because I had any fun at all. It was quite boring.
Alrighty, so
Yeah.
we're at the end here. Let me one last closing slide on this. Is that PowerPoint? No, that's here's the but, no, I think I got it. Well, I thought I had it.
You got it?
Yeah, I know. I thought I had it. And I did that. Oh yeah. Oh, there it is. Okay, and then if I do the Shift F5, we'll come back up at the same place. Shift F5 is supposed to be in the same spot. Yep. Boom. Yep. Okay, that was me and Richard. Fine. Okay, so next Tuesday I will be up there doing that again. That obviously was just for fun for a TV show to generate the basic idea. But the real thing is going to be starting. This actually got funded by NASA to go and now do for real. Our little boxes here are a little smaller this time because we're doing it in a little bit more controlled fashion. A little bit more fancy equipment that we're using, but still GoPros, because they turn out to be the best bang for the buck to getting the imagery we want. We've got 8 boxes this time filled with things like enstatite and pyroxene and a crushed up carbonaceous chondrite meteorite and so on. And we'll be doing exactly that same sort of data taking this next week, next March, next November, and the March after that. We got 4 flights funded to go and do this with a wide range of stuff. We're going to be looking at how does this process depend on the size of the particles in the box. A millimeter across, half a millimeter across, quarter millimeter across. How does it depend on how many particles are in the box? How fast does that clumping rate go? You might expect that if there's more particles around and interact with each other, you might form more clumps faster than if there's just a few little things floating around. We're going to look at the dependence on the particle number density. Also the particle composition. Is the olivine going to clump more efficiently than the enstatite, which is a type of mineral you find in like lava rocks? All that kind of stuff. So trying to answer the real questions, not just playing with sugar and salt and coffee. So that starts next week, and that'll be 0G flight number 11 for me of all things, believe it or not. I've now spent basically more than one entire. If I could put it all together continuously, I've now spent more than one Earth orbit in 0G. Any of you can go and do this. Actually, 0G, the company that does this for research purposes. Any single one of you can go and buy a ticket to go fly that aircraft, fly on that aircraft, and get 0G as well. It's an amazing, magical experience. Skip your European vacation and go do this, okay, for the same price. I'm sorry?
How much is it?
About $5,000 for the ticket for the flight. That's a European vacation. Skip the European vacation, go get this once-in-a-lifetime experience. It's amazing and it's
How
magical.
many, and
So-
you, oh, go ahead.
So can you detect or measure the electrostatics?
Yeah, that's what we think we can do by measuring the rate of accumulation that's going on there. There are going to be some complicating factors that we are not yet sure of. These are plastic boxes. Plastic is well known to have some electrostatic issues. But we think we've convinced ourselves that given the scale of what's going to happen, the little bit of static charge on the walls of the thing aren't going to affect too much what's going on in the middle. And so but that's why they call it science. If we knew what the answer was going to be, we wouldn't have to fly it. So we're gonna see what happens. Yeah, seriously though, we think we can by quantitatively measuring all these things from the video. We have two cameras looking from orthogonal directions for each box, and by measuring statistically that clumping rate, we'll go from frame 0 where nothing's happening to the end, and kind of measure the sort of the pixel area taken up by growing clumps and measure that as a function of time. We think from that we can start to discern some of the basic properties of what's the strength of the clumping based on the static charge and so on. So we'll see. Time will tell as we actually do the analysis.
Do you have any micron or 10 micron sized particles in there, and are these sifted for uniformity?
Yeah, we very carefully have sieved and sifted all this stuff out. For various reasons, we're trying to keep the very, very, very finest dust out of there. Part of it's a safety issue. These boxes have to be vented. You can't quite see, well, you may be able to see right there. And each of these boxes is a little vent hole there. You're flying in a pressurized aircraft. You can't have a completely sealed box in a thing where the pressure changes to the box we don't want the boxes to go pop and then everything goes flying out. So they have to be vented. But we put filters over the vents, but the filters still have to let air in and out, which means if we go to really, 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 really fine stuff, like 10 micron sized particles, that's fine enough where even maybe some of that stuff might get poofed out, and we just don't want to do that. So we've limited things to kind of like 125 microns. So about an eighth of a millimeter across. So we've pre-sieved out. We've got certain very fixed size fractions of very particular minerals that we've chosen to try to set them. And what we've done is we've tried to set, okay, here's we've got 8 boxes. One box has got like what we consider sort of our baseline particle size and particle concentration. And then from there we say, okay, let's say we have the same concentration but smaller particles, the same concentration but larger particles, the same size particles but fewer of them, the same size particles but more of them. We've kind of tried to branch off from that systematically for this first set of experiments. And we'll see what we get, and then next March we'll adjust and fly different stuff. So the lesson is, I saw some young folks here.
Yeah.
The lesson is you can do fun stuff in planetary science. You can blow stuff up and shoot stuff and go fly in 0G and go fly jets, and it can be a pretty exciting world, and it's science, folks. It's fun. We're trying to figure out how the universe is working, and that's fundamentally what it's all about. And you have fun as you go. So thanks.
Thank you.
I have a quick question. On your experiments, on the momentum on the,
Yeah.
on the asteroids. The ferronickel,
Yes.
I guess that's what it is, does that exhibit molten metal
Yeah, we do. We see it.
particles that come off?
Yeah,
of
we see it in the high-speed video. Some of the cameras we shoot. Well, so we've got these cameras called the camera company. High-speed things on TV. Most of the video shots we do are at measly 3, 4, 5, 6,000 frames per second. But a couple of the Japanese-made Shimadzu high-speed cameras that we shoot at the Ames gun, we aim 2 of those at each of our shots, and particularly the metal ones we were doing this. We can shoot 1,000,000 frames per second on those. And so what you see is the actual project at 5, 6 kilometers per second. You see the projectile come in and merge to the surface, and you see the actual crater forming and the jets of molten metal spraying out. And we can track where things go. It's just absolutely phenomenal data.
There should be a chemical reaction on that molten metal.
Yeah, there are. Well, we shoot in a partial vacuum. It's not in air,
Okay.
but it's not a pure vacuum. And
But in
yeah,
air,
absolutely.
There'd be a violent reaction.
Oh, well, yeah, absolutely. And we're shooting quartz projectiles. We see remnants of the melted quartz in the floors of the craters. We've particularly been focusing on those nickel-iron ones, not because they're important from the perspective of the global impact threat. There are very few nickel-iron asteroids out there. It's only a few % of the impact threat. But because we do have a spacecraft now going out to the asteroid Psyche, we've never seen out in space, up close, what the morphology of impact craters and regolith looks like on essentially a nickel-iron object out there. And so we've done now a set of, we're just getting ready to submit the actual scientific paper on this. I think we've got a library now of 60 or 70 impacts we've made now in metal like this to look at the morphology. We've even done ones where we've taken one target and shot it like 15 or 20 times and just kept overlaying the craters to kind of see what's a cratered surface look like in metal. We've never seen that before in space. There's a big literature of impacts into metal, high-speed impacts into metal out there. Because there's a certain branch of humanity that's very interested in what happens when projectiles hit
That's
metal,
exactly
right? But that's in a branch of literature that most of us are not privy to see.
But
And so from a scientific perspective, we've now begun those first ones that are out there in the literature for us to look at.
It looks like a mining technique to me.
But Larry,
It's fun.
what you're involved with,
Molten metal
explosives.
explosives.
Yeah.
Yeah, okay, yeah, like the shape charges, copper, yeah, exactly. Yeah, we're seeing all that fun jetting stuff, yeah. Yeah. Alrighty, thanks everybody, enjoy the snack.